Let's turn our attention away from geometrical optics and move toward looking at physical optics, or sometimes called wave optics. And but before we do that, let's review some wave phenomena that you probably have seen before. Waves are kind of strange creatures. They're collective phenomena. You can't have a wave if there's only one particle, so it takes a coordinated interaction over really long range, a fairly long range, to develop a wave phenomena. But their waves occur everywhere in nature, and they were most carefully studied initially with water waves, but it's since gone to sound waves and seismic waves, and for us, light waves, but any number of physical applications for this general concept of a wave. First thing we should do is, well, what is it that's actually going through the system? And that's a kind of a difficult thing because it always involves some abstract quantities. But waves are essentially disturbances from an equilibrium condition that propagate physical properties over remote locations, from one location to another over long distances. And these physical properties are generally things like energy and momentum and angular momentum, density. So they're different quantities that have some physical context for the problem at hand. But what I'm going to first look at would probably be called a wave pulse. And if you like, you can think of this as just an arbitrary function here, whatever that function that describes that. And y as a function of x is just f of x. You might think of that as a photograph at time t equal to 0 of maybe a tsunami or something, a big pulse that's traveling from left to right. And in any event, if it's moving and I come back and take a photograph of it a time t later, so this one's at time t equals 0, this photograph is at time t, then what's happened is this tsunami, the tidal wave, I guess, has in time t moves in general a distance that's velocity times time. If it's moving with velocity v, then if then this picture was taken at time t, then the distance that peak has moved over from where it was originally is just v times t. And if I want to describe that, this wave, as a function of time, it's fairly easy to do from my original coordinate system. If I want to look at any point on this wave, and that would be the distance from the origin to this point, which would be x, so I'm at the point x, I could think of that as having a translated coordinate system is translated by this distance v times t to the peak of that wave and measuring it as x prime. But I know when I'm centered on the wave that if it's propagating without distortion at a constant rate, which I'm assuming here, then that the function I'll get plotting it about x prime is the same as this function that was up here when I took the photograph at time 0. So for a distortionless wave, this new position is f of x prime, where x prime is measured from the central bulge. But pretty clearly, if I look at this total distance, x, from the origin here to this point, that's just x prime plus vt. X prime, x prime plus vt. And so x prime is 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 x minus vt. Total distance is x, and if I subtract vt from it, then I get this remainder, which is x prime. So x prime is x minus vt. and I can then plug that in up here for the description at this about that point, and I get y, the height of the wave, is equal to f of x minus vt. And so this is a traveling wave that's moving in the positive x direction with a constant speed v. And I'm also assuming there's no distortion or attenuation of the wave on this. So this is sort of an ideal case. But the tsunamis or tidal waves like this, they can go for very long distances and maintain their form. So certainly many kilometers, even hundreds of kilometers in certain configurations. Now, if you look at that, this y now is a function of not only x and t, and that will give me, assuming I'd gotten this original photograph and I'd fit it with a nice curve here, that would give me the height at any time x and any time t is just my original function times this x minus v as an argument of x minus vt. So these are traveling waves. I won't go over it much, but I could certainly let v have the wave travel in the opposite direction. So a wave going to the negative direction, I would just take this solution and replace everywhere there's a v, replace it with minus v. Since originally we had the wave going in the positive x direction. So if I change its sign, change the sign up here, then I get a wave that looks like this, x plus vt. So a wave traveling in the positive x direction would look like this pulse, and one going in the minus x direction with the same speed as this. And usually I will I'll lump those together. Whatever this function is, it just has to be twice differentiable for us, at least as far as we're concerned in this class. It travels. If I choose the minus sign, the wave is moving in the positive x direction. And if I choose the negatives, if I choose the positive side up here, it's moving in the minus x direction. So you got this sort of flip in sign. There's some terminology with this. This argument of this arbitrary function at this point is usually called the phase of the wave. And we'll extend that a little more. For this traveling wave pulse, I can take a picture of it at one instant of time and then take another picture of it at later time at t plus delta t. And during that time, the peak has moved over a distance delta x. And so I can compute, if I measure these two things, the delta t and the distance it's moved, I can get the wave velocity, which is delta x over delta t. Ultimately, is letting delta t get very small, and so you get the instantaneous wave velocity. If you look at that up here, you can rearrange that to get the delta x is equal to v delta t. Or if I take this over to this side, I get delta x minus v delta t equals 0. And now then, if I look at this wave at some later time and at some position x prime, I know that from the previous, I'll look at one that's traveling to the right. It's simply x prime minus v of t prime. But x prime is going to be x plus delta x, and t prime is going to be t plus delta t. So this is where it was at time t plus delta t, and the x was be the original point here, and so the point over here that the peak has moved has moved over from its original x position, x, to x plus delta x. So x prime in this expression is x plus delta x. T prime, it's at a later time, so it's the time for the original photograph plus delta t. So I substitute those in for x prime and t prime. Recollect terms. X minus vt, I keep those. And then delta x minus v delta t here. But that's just equal to 0. And so what I find is that this is f of x minus vt is just y at time x and t. Now I'm focused on a very specific point, namely this peak. And that peak is at constant phase. And that's something that the eye just tends to do. When you see motion of waves, you tend to focus, it draws your attention to the peaks of it, and you can compute the velocity of them from considerations just by looking to see how far the peak has moved in a given time. But that's the following. When I'm looking at the peaks, the phase x prime minus vt prime is kind of faded out there, is equal to x plus vt. So the phase is the same in this calculation up here, looking at these two phenomena, namely the peaks at different time. And as a result, that leads to this constant velocity v, that we can compute in this fashion, delta x over delta t. And as a result, the wave velocity is probably better called the phase velocity. If you look at this, the phase is x minus vt. If I take a differential of phase, it's just dx minus v dt, assuming the velocity of the wave is constant. And now that if I'm looking always at the same phase, at the peak, where that's always the same number, then this becomes 0, the differential in it. And solving this for the velocity, I get dx dt. So wave velocity is more appropriately called phase velocity. But you see both terminology. Sometimes when you want to emphasize one aspect or another, you use phase velocity. Well, one can look at the wave equation next, which I will turn to. And I'm going to be looking for a wave that's like a pulse. And I could use plus or minus here for the plus or minus. And this factor inside here, plus or minus, is just the phase. And I take derivatives of y with respect to x. So I take two derivatives. It's just going to be, using the chain rule, is just going to be f prime d phi dx. And d phi dx is just 1, so this becomes f prime. Take a second derivative of it, and I do likewise. I take another derivative, d phi dx, again is just 1, and so I get the second derivative with respect to y. Partial derivative is phi prime. And I can do a similar thing for the time derivatives. Again, just use the chain rule to find that one gets plus or minus v, because the phase has that plus or minus v factor in it. And then take another derivative to get the second derivative, and I get, again, use the chain rule, and I'll get another factor of plus or minus v. And then when I multiply these, it doesn't matter. You'll get v squared, either plus plus or minus minus to get the v squared. And then if I use 1 and 2, so I use the fact that f double prime is y partial with respect to y squared. Then that just substitutes here, and I get the wave equation. Now I've removed all expressions for that arbitrary function that I have for the pulse. And that is simply the one-dimensional wave equation. In 3D, it generalizes pretty nicely into this form, where the operator here is just the Laplacian, and so you get the three-dimensional wave equation in that form.